All right, now a bit of chemistry today. Acids, bases, and salts. And this is the IGCSE chapter, acid, bases, and salts. So, what are acids, what are bases, what are salts? That's the first topic that we're going to discuss. And this chapter is basically being divided into reactions of acids and what acids are and how to identify them. And the same for bases, and then salts, which is basically preparation of salts. So let's start with acids and bases. Acids are nothing but proton donators or donors, whatever you want to use. And HCl, for example, if you take HCl as the acid, when it is dissolved in water to form an aqueous solution, the hydrogen it is completely dissociated into H plus ions and Cl minus ions. Hydrogen atom, not molecule, is nothing but one proton and one electron. The H plus ion will basically lose that electron to give us a single proton. So basically what happens is that acids simply dissociate into a proton and a chloride ion in this case, or basically an anion. So therefore they donate that, and that electron, that proton is basically accepted by the base, and therefore bases are proton acceptors. But how do they accept those protons? Well, bases have a criteria, which is basically that they must have OH minus ions in the solution, that is. So alkalis always have the OH minus ion present, and that OH minus ion, for example, in NaOH. If you have NaOH as the base, that will dissociate into Na plus and OH minus ions. This OH minus and this H plus will react to form water. That is how protons are accepted by bases, and that is how the neutralization reaction works in general. So like I said, bases which are soluble in water are known as alkalis, and for a solution to be acidic, there must be H plus ions, and for a solution to be alkaline, there must be OH minus ions. Next, acid reactions for acids. So metal plus acid gives us salt plus hydrogen, acid plus base gives us salt plus water, and metal carbonate plus acid gives us salt, water, and carbon dioxide. So let's give some examples for each of them. Let's say the first one is the first one is metal plus acid. So let's take sodium plus hydrogen chloride, hydrochloric acid, which will give us what? NaCl plus H2. Now, to balance this equation, we need 2, 2, 2, like that. Now, acids and base, that is a neutralization reaction. Okay, one thing is that acid reactions are all exothermic. So that means when you have an acid and metal reacting together, there is hydrogen released and salt released. Salt is formed, right? The salt is going to be, this is a soluble salt, so it's going to be aqueous. This is going to be aqueous. This is going to be solid, and this is going to be gas. But basically, it's going to be an exothermic reaction, all of them. Acid reactions are always exothermic, all of these at least. And the next one would be metal acid plus base gives us salt and water, which is a neutralization reaction. So here I'm going to have NaOH plus HCl. That will give me what? Sodium chloride. Previously discussed, OH minus and OH plus will give us H2O. That is a reaction which is known as neutralization. Now, metal carbonate plus acid, let's take sodium carbonate, so Na2CO3 plus acid is again hydrochloric acid. This will give me NaCl, so sodium chloride, plus carbon dioxide plus water. Those are the three reactions that we need to know for acids. The reactions we need to know for bases is neutralization, like we discussed in the previous slide, and also the base plus an ammonium salt. And this base has to be an alkali. So this has to be an alkali, which means that it has to be aqueous. All right. So the ammonium salt could be, well, ammonium as an ion has a charge of, ammonium is this, NH4 plus, it has a charge of 1 plus. So let's take an ammonium salt, let's say ammonium sulfate. And let's say the base is NaOH plus ammonium sulfate, right? So NH4 twice SO4. This will give us a salt, water, and ammonia. Ammonia is going to be NH3, that's the gas. Water is H2O, so that's the easy part. The next one is going to be sodium sulfate, which is going to be Na2SO4. All right, those are the 5 reactions that we need to know of. Technically, it's 4 reactions, but That's it for acids and base reactions. Now, one thing that I'd like to discuss is the applications of neutralization. So sometimes what happens is acid rain, right? To fight against acid rain, or to basically make sure that the soil, for example, doesn't get completely contaminated with acid, with acidic ions, um, what we do is we lay out calcium carbonate or calcium oxide, which is limestone or lime, right? So if you were to look at the reaction between them, it should be something like this. So this is calcium carbonate, and let's say that the acid in that acid rain gave us, let's say, nitric acid, HNO3. Well, we see the reaction is going to be something like calcium nitrate, so CaNO3 twice, plus CO2 plus H2O. So this is going to be a reaction, and this is one application of the neutralization process. So let's take a simple neutralization reaction. So this will be sodium hydroxide, NaOH, plus I'm going to take nitric acid, HNO3. This will give us what? So first, this is the reaction. These are the reactants. What I'm going to do is write them in the ionic state. So it's going to be, because they're all aqueous, right? So this will be Na plus OH minus plus H plus NO3 minus. So we know that these two will react to give us water. So I'm just going to scratch that out. Now, if you look at it, the anion from the acid is nitrate, and the cation from the base is sodium. They will react together to give us what? NaNO3. So that's the salt. That's the formation of the salt. The salt is going to be basically unreactive. This is going to be soluble because all nitrates are soluble. We'll get to that later. So this will be an aqueous solution with water in it. All right, that will be the final output of this reaction. All right, next. The different cations and anions that we need to know are the chloride ions and the fluoride ions, and basically they are known as the halides. So this will be Cl minus, F minus. They basically have a charge of 1 minus. Hydroxide is OH minus, similar to chlorides, they are 1 minus in charge. Hydrogen carbonate is not necessary, but they're good to know. So HCO3 minus. And then sulfate ion, it's very common. Carbonate is also very common, and so is oxide. Then phosphate is PO4 3 minus, and the ammonium is the only cation that we need to know of other than the metal ions that they form themselves, which is going to be NH4 1 plus that we discussed before. So the different indicators, the best way to do it is just to mug it up. There's nothing else you can do other than maybe testing this out in the lab yourself, which will be pretty beneficial. So when it comes to litmus, acids turn blue litmus red, and they are red in solution. In neutral solutions, which is a pH of 7, the litmus is litmus paper doesn't change, either of them, and the litmus solution will be purple in color. And when it's basic, the red litmus will turn blue, so it will be blue in solution. Thiamethylene will be colorless in acid and in neutral solution, but it will be blue in basic. The pH indicator will be red in acid, green in neutral, and basic will be purple in color. Then methyl orange will have red orange in acid. The neutral will be yellow orange. All right. And we haven't discussed this, but we already know that acids have a pH between 0 and 6. Neutral is 7, and basic is 8 to 14. And basically that's the range for the pH, was 0 to 14. 14 being the strongest base and 0 being the strongest acid, and pH is nothing but power of hydrogen in that solution. Now, strength of acids and bases, and this is basically to do with strong acid, strong base, strong yeah, weak acid, weak base. So let's start off with hydrochloric acid, and basically the idea is that when you have 10 molecules of HCl in its gaseous state and you dissolve all of it in water, you'll get 10 H plus ions and 10 Cl minus ions in their aqueous state. That is the definition of a strong acid, in which all of the molecules are dissociated into ions. There is no partial ionization, basically. And the second reaction over here, which is 10CH3COOH, which, if I'm not wrong, is ethanoic acid. So this we see partial ionization, which means that we'll get 1 mole of either of them, meaning that it doesn't have to be 1 mole. but there won't be complete ionization to give us 10 CH3COO minus and 10 H plus ions. So that difference is what makes it a weak acid. Weak acids are those which have which undergo partial ionization in aqueous medium. Now let's take sodium hydroxide. Sodium hydroxide, if you dissolve it in water, you get 10 sodium ions and 10 hydroxide ions, which means it's a strong base. And NH4OH, that's ammonium hydroxide, so it's technically 4 at the subscript, like this. And this is NH4 plus, like this. Yeah, if you look at that, this is also CH3 in the subscript and subscript. Yeah. All right, so what would this be? This is another weak, this is a weak base because there is partial ionization, right? That's it. So in summary, strong acids and strong bases are those which undergo complete ionization, while weak bases and weak acids are those which undergo partial ionization. And concentration is basically defined in stoichiometry as the number of moles per unit volume. And so if you have, let's say, a concentration of 1 m, that is equal to 1 mole per decimeter cubed, and 1 decimeter cubed is going to be, well, 1 meter cubed is equal to 1000 decimeters cubed is equal to 1000 centimeters cubed, and we can basically divide this by 1000 to get 1 decimeter cubed. 1 decimeter cubed is equal to 1000 centimeters cubed. So those are the conversions that we need to know of. Concentration can be written in grams per decimeter cubed as well, which will be using the formula that moles is equal to mass by mR. So if you know the number of moles, you can write it as well, mass over here instead and convert it further. Then oxides. So oxides are metal oxides can either be basic in nature or amphoteric, and non-metal oxides can either be acidic or neutral in nature. So sodium oxide, calcium oxide, magnesium oxide, for example, are basic in nature, while aluminum oxide and zinc oxide are what they're amphoteric in nature. Amphoteric means that they'll react with both acids and bases to form undergo neutralization, basically to form a salt. Normal oxides such as sulfur dioxide is acidic in nature, and they can also be neutral in nature, which would be, for example, NO, nitrogen monoxide. So now preparation of salts. This is a fun topic, really. We have two types of salts which are soluble and insoluble, right? There is a criteria for the solubility, right? So all nitrates are soluble. All group 1 metal salts are soluble along with ammonium salts. So sodium, lithium, potassium, those salts are always soluble, and so are ammonium salts. All fluorides are soluble except lead and silver. All sulfates are soluble except barium, calcium, and lead. And all carbonates and hydroxides oxides are insoluble except group 1 metals and ammonium. And you have to basically mug this up. This is another thing. Next is the reactivity series, and I have a small mnemonic for that. So it sounds a bit dumb, but please stop calling me a cute zebra. Instead, try learning how copper saves gold. That's the reactivity series. And preparing soluble salts, we basically have three choices. If it's a metal plus acid, then the only problem over here would be the fact that if the metal is too high up in the reactivity series, then the reaction would be very violent, and so we don't use this method. If it were metal carbonate and acid, the main problem over here is that the method produces CO2, which is not good, and acid plus base, or basically neutralization, is when the metal is too reactive. Basically, if you have something like sodium hydroxide, you have to make sodium hydroxide. The best way to do this would be using alkali and acid neutralization reaction, because sodium as an acid is sodium as a metal is very reactive, so we don't want to use this method over here. And this method, like I said, produces CO2, so we basically never use this method. And so we can use base plus acid over here. Let's say we have something like zinc. We could use zinc plus hydrochloric acid to give zinc chloride. That works, basically that. Now preparing insoluble salts. So the method to produce insoluble salts is known as the precipitation reaction. And the reaction is basically a soluble salt plus a soluble salt, another soluble salt, will give us an insoluble salt and a soluble salt. Now there's a salt over here. Yeah. So let's take the preparation of barium sulfate, for example. The ideal way to do this would be use the precipitation reaction, of course. And using the precipitation reaction, you have to find a salt with which barium is soluble. So if you look at this over here, it says that all nitrates are soluble. So you go here, barium nitrate will therefore be soluble. Yeah. Then sodium sulfate is also going to be soluble because all sodium salts are soluble. And then you get barium sulfate, displacement reaction, displacement reaction. So this is nothing but a double displacement reaction, in which if you have something like AB plus BC plus CD, that will give us AD or AC, and that means it has to be like this. So it's going to be BC like that. If you look at this, barium is A, it is with D, so BD, AD, and sodium, and that BBC. So that's the form. That's the general reaction. All right, now testing for the presence of water, we have two tests for it. So one of them would be the cobalt fluoride, which is blue when anhydrous and pink when hydrated, and this is basically what it looks like in the equation form. And copper 2 sulfate, which is colorless when anhydrous and blue when hydrated. Anhydrous means that there is no water in it, and hydrated means that it is with enough water. Now, I have some questions over here, so let's solve that. So P is a hydrated metal salt with a blue color. So first thing is that it's hydrated and it has a blue color, so it's probably going to be copper 2 sulfate. Anyways, let's read more. When P is heated, water is given off, leaving solid Q. And R is another hydrated with a pink color. Pink means that it's going to be a cobalt fluoride, right? So when R is heated, it leaves a solid S. So the name of P, which is a hydrated metal salt, is going to be copper 2 sulfate. So hydrated copper 2 sulfate. It's going to be one of these two. And the color of S is going to be blue. So the answer is C. Which forms an acidic oxide? So we know that acidic oxides are nonmetals. So these two are going to be cancelled out. These are the nonmetals. But we know that D is a noble gas, so it won't react to form an oxide. So the answer has to be B over here. So this is wrong. So B is the answer. Strong acids are correct. So which statement about strong acids are correct? So they have a high concentration of OH minus ion. This is a strong base, right? A pH value of 1 makes sense. Completely ionized in water, yes. They turn red litmus paper blue, no. So it's going to be 2 and 3, which is C. Okay, so it neutralizes sulfuric acid, which means that it is either amphoteric or basic in nature, right? So there are only two options over here, so it has to be basic. And metal oxides are basic in nature, so it's going to be a B here. Burning fossil fuels releases sulfur dioxide, which leads to acid rain. Which ion in the rain causes it to be acidic? H plus ions. And this question is about salts. This is a theory question in which you basically have to describe how you make a pure sample of lead iodide by precipitation. So we know that lead iodide is insoluble in water. So we have to make use of the precipitation reaction in which, so I'll just tell you the pointers. The first point will be that in the precipitation reaction, we have to use a soluble and we have to use two soluble salts, which in this case would be lead nitrate and sodium iodide. And basically we have to put them together in a beaker and just mix them. When you do mix them, what you will see is that the reaction will take place, the double displacement reaction will take place. You have to write down the equation as well. So this will be PB and you have to balance it. You see, this is twice and this is twice, and that does it. So that's the balance equation. Next thing you can do is write down the state symbols as well. So this is going to be aqueous, this is going to be aqueous, this is going to be solid, and this is going to be aqueous. So that's going to be another step. Next, you basically have to write how you're going to stir it, and the PbI2 is going to get settled at the bottom, and basically you will stop stirring it, and the reaction will end. You'll know that the reaction will end basically when the solid at the end stops being collected. So when the collection, then there's no more residue being formed, the reaction is done, and then you can use a filter paper and filter it, and using that you can just let it dry. But now it says a pure sample of that by precipitation. It doesn't say that you need to crystallize it or anything, otherwise you can write down that process as well. Now, one last thing I'd like to discuss is about this. Yeah. I talked about over here how the electron is lost, but where does it go to is the question that I want to answer. So I'm just going to erase everything on this slide and draw HCl. We know that HCl is a non-metal molecule, so it's going to be a covalent compound, something like this, and hydrogen is going to close, and it's going to be like this. This is what it's going to look like. Now, I said that it dissociates into H plus ions and Cl minus ions. So for that to happen, for the chlorine atom over here to become chloride ion, it has to gain that extra electron. So what happens is the chlorine basically pulls away that electron from hydrogen, which was being shared mutually, and so we get Cl minus because that electron will now belong to chlorine. So it will now end up being something like this. So that'll be the formation of Cl minus, and that'll be the formation of H plus. That is the main reaction that takes place to in the process of dissociation. That's it. That's all we need to know for acid, bases, and salts. And thank you for watching.